All right, chemists and other friends, welcome back to Chemistry 132B. This is lecture 19 already, and this will be a continuation of the material we have been talking about on Friday. But I have to say that this particular lecture and also the lecture on Wednesday will not be part of the midterm material. So the midterm will be on Friday. It will be conducted in Canvas in the same fashion as we have done for the first one, with some additional controls to prevent people from posting the questions on all kinds of platforms. So we're going to make sure that that's not happening again. The material will be everything that we covered up until last Friday. So basically, the lectures 11 to 18. Those are the lectures of relevance. That's the material that you can expect on the midterm. So today's lecture is not going to be part of the midterm, but it is going to be important for the final, which is coming at us at an alarming pace already. So because the end of the quarter, I can already smell it. It's pretty close. So this is actually a very important part of the final topic of this course, which is really molecular orbitals. So molecular orbitals is the last topic of the course, but there's many things we can say about it. And so today we're going to dive into some really, really important stuff, really the basics of understanding the energies of molecular orbitals. The practice midterm will be posted this morning, right after the lecture. So yeah, just in the same fashion as last time, there will be a practice quiz, which is representative of the questions you may expect for the midterm on Friday. It is basically a collection of 2 previous midterm exams. Okay, so again, these are true midterm questions from previous years, same level of difficulty, and we combined 2 into 1. So this practice quiz is twice as long as the actual quiz that you'll be getting on Friday. So I'm gonna, open it up this morning so you can have a look. Make sure you do the exam in a kind of a real way, so you don't really look at the answers first and then try to solve it, because that defeats the purpose. So try to use it as a real exam. Okay. Okay. If I have updates about the first midterm and how we're going to do that, I'll let you know. Okay, so currently it's processing and we get closer to the end, but I don't have any real updates at this point to disseminate. Okay, I'm going to dive in, folks. So fasten your seatbelts. This is going to be quite important for people who aim to be theoretical chemists. Some people like to do that. Then this is a very important lecture, because we're going to talk about a principle that we apply to determine the energies of molecular orbitals. This is the kind of the principle that people use all the time. And if you are an organic chemist and you don't really care about any kind of computation, then this is still interesting, because you should know really where these things come from. So if you work with a theoretical chemist and he or she gives you some results, then at least you should know where these results come from. And so today we're going to talk about something quite fundamental. Okay, so here is the situation. We have, we have moved away from the single atom picture. So far, up until Friday, we have talked about individual atoms and determined their energies. We talked a little bit about valence bond theory, which basically explains to us how we can think of orbitals directed in space by making combinations of atomic orbitals, but it's still a single atom picture. Here we're going to have a picture where we consider the input of 2 atoms, where we consider atomic orbitals from each of the atoms, here atom A and B, and they are going to be combined in a certain way. Okay, and we're going to try to find today the energies that will result from combining orbitals from individual atoms together. That is a very important question. What does that produce? Tentatively, what we will expect is that we will find an orbital that's lower in energy than the individual atomic orbitals, and orbital that is higher in energy than the individual atomic orbitals. Those are the bonding and the anti-bonding orbitals. The lowering of the energy of the bonding orbital is the reason why there is a bond in the first place. Because if there's no lowering, there's no reason why these two particles should engage into a bond, right? So that is really the result we expect, but we have to prove it. And to prove that is a little bit of work. So we're going to do that today. The most important realization is that this new system of two atoms in close proximity needs to be described by a new Hamiltonian that includes all interactions between the charged particles, meaning there's interactions between the nuclei, A and B, and there is interactions between the electrons from A and B among one another, okay? So in between the two atoms, there's interactions of the charged particles, in addition to the interactions that were already there within each atom. So there's a new layer of interactions here that will make the description very complicated. And so what we have done on Friday is that we say, well, forget about that, okay? Because this new Hamiltonian is so complicated that I have a really hard time finding its solutions. And that is generally true. It's really hard to find analytical solutions, if not impossible, of this new Hamiltonian. If you would like to solve the Schrödinger equation with the new Hamiltonian, you find out that you'll have a hard time, unless you have a good computer, and of course then you can get pretty close, but you still need approximations, and that's what we're going to talk about today. The general recipe is to say the following. I'm going to make a linear combination of the orbitals of each atom, atom A and atom B, and that's what you see here. I see here psi plus minus, that is the bonding and the anti-bonding orbital, as we talked about last time. Okay, and right now I'm going to make it a little bit more general. I'm going to put a coefficient here and a coefficient there. This is the weight of the orbital that's contributed by A, and that is the weight of the orbital contributed by B. They don't have to be the same. On Friday, we kind of conveniently assume these coefficients to be the same, but they don't have to be the same, as you will see later on today. So this is, of course, the wave function from particle A, and this is the wave function from atom B. And the most important notion here is that what we assume, or what we start from, is the fact that these two orbitals are hydrogenic orbitals, the same orbitals we have considered for the single atomic picture, okay? So that's what we assume. We assume the unperturbed individual orbitals as inputs into our new function, which is a linear combination of both. These individual hydrogenic orbitals are not eigenfunctions of the Hamiltonian because they do not include all the interactions. So these wave functions here, individual unperturbed atomic wave functions, are not eigenfunctions of this new Hamiltonian, H. Okay, this guy includes all interactions. These hydrogenic orbitals were solved from a Hamiltonian that did not include all these interactions. So clearly, wave function A and wave function B are not eigenstates of the Hamiltonian, and that complicates the situation quite a bit. So how do we find energies then if these A and B are not eigenstates of the new Hamiltonian? I mean, how do I get to an expression for energy? Because I need to operate on these states with H to find energies. So how do I do that? Okay, so that is what we're going to talk about right now, because we're going to do that through a very important principle, which is called the variation principle. You may have heard of it in a different course. So I'm going to talk about it. It's a little dense, so don't be afraid, okay? You don't have to reproduce all of this, what I'm going to show you, but try to follow the argument, because the argument is really important. That's the physical understanding I hope you'll take away from this. The general notion is the following. If I have my Hamiltonian, so this H with this little hat is, of course, my new Hamiltonian, which includes all interactions, right? If for some reason I am very smart and I can find the wave functions of this Hamiltonian, these two guys, okay, then if I calculate the excitation value, I know that I find the lowest energy, because this sign 0 is what I think is the ground state. So if I find that ground state, if I find an expression for that ground state, and I operate with this Hamiltonian on the ground state, I generate the ground state energy. Okay, and since this is a normalized wave function, what I find is simply the ground state energy. Okay, the expectation value for the ground state is the eigenvalue for the ground state of the new Hamiltonian. That's great. That's what I want. I want to find the ground state energy of my atom, ideally like so. But the problem is, I do not have these eigenstates of the Hamiltonian, which is what I just said. I don't have them. It's too hard to find them. So how do we get to the ground state energy then? Well, what we can do is the following. Remember, what I'm going to do is I'm going to make a linear combination of other things. Okay, so I'm going to compose a wave function, which I'm going to call trial. I'm going to try something. I'm going to say, well, I'm going to, make a linear combination of other wave functions, and then I can try to get very close to what this psi naught should look like. The psi 0, which I call psi naught, is what I really want to find, but I'm going to try to approximate it by making a trial wave function, which is a linear combination of other wave functions. Now, we're going to see several ways in which we can do that. But for the sake of argument here, I'm going to say, let's say that I make a linear combination of the eigenstates of the new Hamiltonian. Okay? Well, I do not know these eigenstates, but this is a theoretical exercise. So let's say I do know these. Okay? Let's say I do know these states. These are the eigenstates of the new Hamiltonian that I have no access to. But for the sake of a theoretical argument, I can make this statement nonetheless. I can say any trial function can be expressed in a linear combination of eigenstates from a complete set. That is one of the most basic things that we have said in this course, right? So that is still true. I can make any kind of function in terms of a complete set of eigenfunctions. This is always true. This is always true. Okay, so keep in mind, because on the next slide, we're going to do things slightly differently. But here, this is a general statement. So here, everything is still very general. Completely theoretical, because I do not have these functions. Okay, but let's carry on anyway. Let's say I'm going to try to have an approximate solution, and any function, since I can describe any function in terms of a complete set, that's what I'm going to do. Okay, so here we go. What I'm going to do then, I'm going to say, of this approximate wave function, I'm going to calculate the expectation value for energy. And I'm going to try to get very close to E naught. Okay, that's what I'm trying to do. So I'm going to calculate this expression. That's the energy of the trial function. I want this energy to be very close to E naught. So I'm going to just fill out the expression for the wave functions. I just have an expression here above. I'm going to plug them in, and we have done this several times now. This expression we have done several times in this course earlier on. And so it should be no real mystery then that you get basically this. You get this product of the coefficients, and then you get this integral, right? With n prime and n, because I make dummy indices for these summations. Okay, so one I call prime, one I call n, just to be able to discriminate them. So this is what I have to calculate. Well, the good thing is I just said that these guys are eigenstates of the Hamiltonian, theoretically, right? So I can operate on this guy and generate an eigenvalue, which is going to be En prime. So there it is. That is the En prime right there. Hopefully you can see it. There it is. Everything else stays the same. Now this psi n and psi n prime are just an integral that, of course, is going to be a Kronecker delta, because these n's have to be the same. So what I end up with is this. These two n's have to be the same. So the coefficient n modulus square is what I'm getting, times the ENs. This is also a solution we have seen before. But now we're going to try to give it some physical meaning, because it's very important what comes out of it. Basically, what this expression says is this. If you have a trial function, so not the real deal, but a trial function, then what you find is that the energy of that state is going to be a summation of the energies of the original states of the Hamiltonian with weighting factors. Okay? Now, since I'm interested in finding the ground state energy, that's given over here, I want to find this guy, right? But unless I choose the right wave function, only this one will give you this guy. So if you don't choose the right one, but you make a linear sum, the contributions from all other psi ends are going to be higher. That's given over here, right? So the lowest energy is over here. This is going to be psi naught. It's going to be psi 1, psi 2, psi 3, and so forth. You go up, of course, on the ladder. So as soon as you mix in contributions from other wave functions, you're going to add energies to the lowest energy that is going to make the total higher. Okay? What does that mean? That means that what you're going to find is that you find either E naught, if you choose by accident psi 0. If you know what that is, then you're going to find the lowest energy, but you don't know what it is, and therefore you add more energies from other wave functions because you have a sum over all these wave functions. Each one contributes a little bit of energy. So the overall energy that you'll find is going to be the same or more than the ground state wave function energy. That's what this expression says. Okay? This is very important because this statement says as soon as you are going to work with a trial wave function, then your energy that you're going to find is the same as the ground state energy of the true system. Okay, if you chose accidentally your trial wave function to be the ground state wave function of the system, typically you don't know that. Instead, what you're going to find is you're going to mix in energies from other states, adding to the total, and therefore you're going to have more energy than the ground state energy. That's what it says. This is the variation principle. It says that the energy that you're going to find is going to be more than the energy of the ground state because you don't know the exact expression of the true ground state. As soon as you don't know that and you're going to try something else, you're going to find something that is more than the ground state energy. That is the variation principle. We're going to use that principle to try to minimize the energy that we're going to find, to really push it down to the bottom so that we're going to get a wave function that is going to be the closest possible description of my true system. That is the goal. Okay, so any trial wave function will give a higher or equal value for the energy expectation value than the true ground state energy. That is the main guiding principle here. What I'm going to do, I know, whenever I'm going to try something, I'm always going to find an energy that's most likely higher. By minimizing this energy, by doing something to the wave function, I'm going to minimize something of this wave function. I'm going to try to minimize this energy. Okay, that's what I'm going to do over here. So this is called the Rayleigh-Ritch method. Rayleigh-Ritch method. And we're going to have the trial wave function again, but now I'm with an important difference. Okay, now I'm going to say these i's here are not the eigenstates of my Hamiltonian. The Hamiltonian was, this general Hamiltonian, H. I don't know what these eigenstates are, so it doesn't make a lot of sense to do an expansion in terms of those eigenstates. Instead, I'm going to say these i's here are now different states that I do have access to. For instance, the atomic orbitals of the individual atoms. I'm going to make a linear combination of atomic orbitals, hydrogenic orbitals of my individual atoms. So this is not going to be now a complete set. These i's don't form a complete set necessarily because they include wave functions from other atoms, okay? But it's still a trial function and the variation principle still holds. That theoretical concept still holds. So if I put a trial wave function in this expectation value for the Hamiltonian, I'm going to find still an energy that is higher than the ground state. So by pushing the energy lower, by making a variation in this wave function and pushing the whole thing lower, I can find the best possible wave function and the lowest possible energy. So that is what we're going to do. If these i's are not eigenstates of the Hamiltonian, their overall expectation value for the energy is going to look like this, right? This is the most general expression for the expectation value of energy using my trial wave function here. Okay, so this is hopefully nothing new. We have done this several times now in this course. Basically, it's this integral divided by this normalization integral here in the denominator. Okay, so that's what I want to calculate. Let's fill it out. I'm going to have these I functions, which are now not eigenstates of H. Okay, they're not. They're just linear combinations of atomic orbitals that are hydrogenic. Okay, so what I'm going to get here is the following expression. These are the coefficients from these wave functions in the integral. And then here at the bottom, I simply have ij with their coefficients. This ij is not going to be necessarily 0 because these I and j correspond to orbitals from different atoms. So this is not going to be 0 here in the denominator. This is a really important difference from the previous slide. But the variation principle is still the same conclusion, because whatever trial wave function I'm using, no matter what the origin, the energy I'm going to find is always greater than the ground state energy, or equal, if you're very lucky. Typically, we're not. Okay, so basically, I'm going to clean up this thing a little bit here. These integrals, I, H, J, I'm going to simply call H, I, J. Okay, so this is a shorthand writing of this integral right here. This H, I, J is also called a matrix element. So I'm going to use that nomenclature also as I move along. Okay, so H, I, J is this integral, but this is also a matrix element of the Hamiltonian. This is the same, okay? If they're equal on each end, then it's H, I, and then I, J, this integral here is the overlap integral between wave function I and J, and that's S. S is not necessarily 0 because I and J come from different atoms, and therefore they're not part of a complete set. Okay, so I'm going to use this way of writing and then summarize, and this is my energy then. Okay, my energy should be in the numerator. I get a summation with coefficients times these matrix elements, which are integrals, and then in the denominator also a summation over all the coefficients times these overlap integrals. So keep this expression in mind because it will come back to us on the next slide. Okay, so this is what it looks like. This is what the energy looks like. The expectation value for the energy looks like this. Now, what I'm going to do is I want to minimize this energy. I want to make it as small as possible. Okay, because that means I'm going to push it closer and closer to the ground state energy. I know this energy is most likely going to be too high. I want to make it smaller. How do I do that? Well, by fiddling with the coefficients. By fiddling with these coefficients, changing their values in such a way that this energy is going to go down. Okay, that's all I can do, because as soon as I choose my set on my linear combination, the only thing I can change is the value of these coefficients. Can I play with these coefficients in such a way that this energy is going to go down? So what I have to do then is to basically take the derivative of the energy with respect to the coefficients, the values of the coefficients, and then set the whole thing to 0. Right? That's what a minimization is. You take the derivative, you look for the 0 of the derivative, which means you look for the minimum. That means you look for the minimum energy, minimizing the energy by finding the right coefficients for the C's. I call it CK because K is just an arbitrary, index from this summation. Okay, so I'm going to have to kind of do the minimization with respect to all CKs that are part of the sum. Okay, so on the next slide, what I'm going to do is I'm going to evaluate this expression. Okay, I'm going to evaluate this expression, and then you will see it will be quite dense, but let me step you through it. Hopefully this will be clear. So here it is. What I'm going to do is I'm going to take the E. This is the expression for E between parentheses, and I'm going to do a derivative with respect to one of the coefficients in the sum. Now the sum has I and J, and K is just one element from either I or J, right? So the summation runs over I and J, and K is just one element within the sum. And I'm going to take the derivative with respect to that coefficient. Okay, so that means that I have to do a little bit of hocus pocus to make that work. So, but first notice that the function for energy has two parts. There's a numerator and there's a denominator. So basically there's two functions that depend on C. Okay, so I have to take a derivative with respect to C, and there's two functions between the parentheses. So basically I have to do the same kind of rule for derivation that we always use for a product. So it's a product rule for derivation. That's what we have to do. That's one step. The other thing is we have to deal with taking out the K out of the sum of J and I. Okay, so again, imagine this is a double sum, right? There is a sum over I and sum over j. Now, at some point, I is going to be the value k. And at some point, j is going to be the value k, and that's when I have to take the derivative. I don't have to take the derivative if one of these values I and j are not k. So this means this double sum I can split in two parts. One for when when I equals k, that is basically here. Okay, so now this ci is known has the value k. That's when I take the derivative. And the second sum is the situation for which j equals k. That's when I'm going to take the derivative. All the other terms I don't have to take a derivative of because they're basically constant in terms of ck, and therefore the derivative is going to be 0. So these are the only surviving terms in taking the derivative of this double sum. I basically get two single sums. In one case, the ck is right here, and the other case, the ck is right here. So it originates from I, or it originates from j. Okay? That is the first part. That's the first part. So what I'm going to do is the product rule. What I'm going to say is I'm going to take out this red function here, which is right here. I'm only going to take a derivative of the green part. Okay? So that's the first part of the product rule. And then the second part is I'm going to take the green part, put it in front, and then take the derivative of the second part, which is the red box. That's written over here. Okay, and do the same thing for the denominator. I'm going to split this double sum into two single sums because I'm going to sum either over the situation where I equals k and a situation where j equals k. Two sums now in the denominator. So that is what I have to take a derivative of. Okay, so derivative of the first term, which is the green box, and then a derivative of the second term, which is the red box. How does HIK come from the green box? So so basically what I'm saying here, this first sum is a situation where I equals k, and equals k, and the second sum is where j equals k. So just check it out, okay? If you put I equals k, then this I here is going to be a k. That's this k right here. And when j is equaling k, then I get this term right there. That's where it comes from. You just have to substitute in k for either I or j. This is a little hairy, but if you just go by the book, then this is exactly what comes out, okay? Okay, so now I'm going to take derivatives. I'm going to take the derivative of the green box and then the derivative of the red box. So first the green box. It's not so hard because basically derivative taking respect to ck, the ck is just a coefficient. Everything else is not depending on ck, just this. So everything else is basically a constant with respect to ck. Take a derivative, you basically just take this one out, take this one out, okay? That's what happens if you take a derivative. So what I'm getting is this. Okay, so this is the first term in the denominator. This term right here is just the first term right here. Then after taking a derivative, I basically cross out the ck's and I'm getting this numerator right here. That is the result of taking the derivative of the whole first line. That is the result. You see that? ck's are basically dropping out of the sum because I take a derivative for each term in the sum. That's what I'm getting. And then the denominator, of course, doesn't change because I'm not doing the derivative with respect to the denominator. Now the second line, a little bit more difficult, okay? Because I have now something in a denominator and I have to take a derivative of this thing. So in general, what that means is the following. Just bear with me. I'm going to take this one. I have to take the derivative of this guy, okay? That's pretty much the same as the previous exercise, just to cross out the ck's. Oops, that is going to be this term right here. Okay, that term right there is going to basically derivative with respect to the quantity that's in the denominator. And then I have to basically do the denominator squared with a negative sign in front, because that's what you get. It's basically 1 over x. Take a derivative with respect to 1 over x. What you get is derivative of x and then minus 1 over x squared. That's the same thing here. So that's what you get here. That's why there's a square here. Okay? There's another thing that I'm doing here that is kind of implicit. After you take a derivative after you take a derivative, then I can recombine this sum, multiply it with with itself, and that means I get this square here of just this double sum. So I can recombine, after I cross out the CKs, recombine these single sums back to a double sum, and that's what you see right there. That's the result. This term right here comes from this term right there. Okay? A lot of stuff happening here. But if you really go through it step by step, this is the result. One thing I'm going to point out is this unit, which has the factor E in it. This is the factor E from the previous slide. I'm going to take it out and just write it as E. And that simplifies the expression just a little bit. Okay? So this is what I'm going to take to the next slide, writing the E factor I'm going to take out of this expression, and that's going to simplify my description a little bit. And so what I'm getting is shown here. This is the result. This is the result. I'm going to have in the denominator now simply a single term. The square is gone because I divided it out. That's what the E has been doing. Okay, and then I get two sums that look like this. Two sums that look like that. So the derivative with respect to the energy, with respect to its coefficients, is this expression right here. Okay, it still looks complicated, but it looks a little cleaner than on the previous slide. Hopefully you agree with that. This thing then has to be set to 0. That is the goal. The goal is to make this whole thing 0. Finding the coefficients that do that will give me the lowest energy. That's what we're doing here. Okay, so let's have a look at these two sums, because in principle, if I assume that for the Hamiltonian, if I have the matrix elements ij, if that is the same as ji, okay, then I can simplify these two sums. I can make them a single sum. Okay, because these are all dummy indices. If we can swap the order of I and k and j, then these two sums are going to be the same. The same for s, k, j equals jk. Okay, if that is true, and this is what we will assume this, and therefore these two sums combine into one. And that means for this whole thing to be 0, what I have to find is this. The condition is satisfied if these sums, so that I'm not focusing on a denominator because I don't want s to be 0, okay? It's going to say this, the denominator must be 0, then this condition is satisfied. And so that means that this condition must hold. The sum over coefficients, ci, and then between parentheses, I have hik minus esik. That must be 0. Okay, and this has a name. These are called these secular equations. Strange name, but that's just how it is. Secular equations. If you satisfy the secular equations, you have an opportunity to find the energies. Okay, so let's give me an example of basically filling out one of our trial functions and see what we find for the energies. Okay, so the trial wave function here is our molecular orbital, and I'm going to do the plus version, which means the constructive interfering one. Right? So I have CA and CB. Those are the two coefficients I'd like to minimize to, right? Given the shape of the wave function shown here. So what I'm going to do is I have now basically expressions of the coefficients. I and j are going to be summed over A and B. Those are the two ingredients. The summation is only over A and B. So both the sum here over I simply runs from A to B. Okay? Now what about K? Well, K is also A or B. So let's just do that. Let's say K equals A. Okay? And A and B are simply the keeping tabs of what atom I'm talking about. So I'm setting the first coefficient to A. So K equals A. I can be either A or B. Okay, so in this expression here of the secular equation, K I set to A, and if that is true, I'm going to run I over A and B. Okay? So what I'm getting is this. I'm just filling it out. C, A for the first sum, and then for the second sum, C, B. That's this one. Those are C, A, and C, B. C, A, and C, B. So I'm summing over I. H, I, K becomes, if K is A, the first sum is over I, so HAA minus ESAA, and then the second sum is over B, that's this guy, so HBA, because this is K, that's K, and that is going to be I, okay? In the second case, I is B, and K remains A. So what I'm getting is CB HBA minus ESBA. That thing is 0. That's one way I can make a combination. The second way I can make a combination is this. I can set K to B and then sum over A and B. I get almost the same thing. A little bit different now. CA times HAB minus ESBAB plus, then again, CB, same thing as before, but now the K is going to be B, okay? So look at the situation above. K is A here, it's B there. Same here. K was A here, it's B right there. Okay, so I have now two expressions here. Both are set to 0. Both must be true at the same time if I would like to find my coefficients C, A, and CB. That's what I'm going to do. Remember, this is the whole purpose. I want to minimize or find numbers for C, A, and CB that's going to satisfy this set of equations. Okay, now I'm going to do a little bit of shorthand writing because this gets pretty messy over here. Alpha A is simply HAA. Beta is HAB, which is the same as HBA. Okay, so beta is just basically beta are the off-diagonal elements of the matrix of H, and alpha A are the diagonal elements of this matrix. Okay, so we'll see. We come back to matrix calculations later on, but this is really what we're going to throw in there as we move along. So alpha A is the diagonal elements of the Hamiltonian matrix, and beta are the off-diagonal elements. Same for S. Okay, so I can make SAB equals SBA. So I'm going to make these two off-diagonal elements equal to one another, which is generally true. Okay, and then finally, SBB equals SAA. That is 1, because that's the overlap integral of the individual atomic orbitals with themselves. That is still 1, because they're still normalized relative to one another. Okay, so that's what I'm going to do. I'm going to rewrite these two equations that I have generated using the expression here. Those are the secular equations. These are the two secular equations I'm getting for these conditions. And these conditions were generated by assuming this trial wave function. Okay, it only has two possibilities, A and B, and so that's what I have to sum over, and that's what I've done here. I've summed over these things and generated two equations that both must be true at the same time, and I can write that as follows. If I fill out all these alpha, betas, and s's, what I'm seeing is the following. I can write these two set of equations in this matrix format. Okay, so you just multiply this term by that by CA, the second term by CB. That's the first line here, and the second line is generated by multiplying this element here with CA times plus the element over here times CB. Okay, that's the second line. So this way of writing is simply regenerating these two lines, and both must be equal to 0. So that is true. This condition is fulfilled. This is why we're going to write this in this matrix format. If the determinant of this first matrix, this 2 by 2 matrix, is 0. If that is true, then this condition is satisfied. AKA, both of these equations are going to be 0 if you fulfill this condition set by the determinant. Okay. There are some questions in the chat box about, you know, the summation. I can fully understand why this is not clear at this point, but please take some time. Okay, fill out first K equals A, then sum over I. Second, set k to b, then sum over I. Okay, and then you really generate these equations. Just try it for yourself, and then you probably will see it. Okay. So I'm going to now fill out the situation for hydrogen. Okay, I'm going to make two orbitals, A and B. They're both hydrogen atoms, so they only have one s to contribute. That means basically these two orbitals are the same. Alpha A equals alpha B, same type of orbitals. And so then I'm going to write it as follows. Okay, I'm going to say alpha A is the same as alpha B, same type of orbital, both 1s orbitals. I'm going to try to solve this determinant that we just derived on the previous page, multiply it out, and I'm collecting terms for E, the energy. And that's what I'm going to do here. So solving the determinant, that's what I did. I'm going to multiply this thing out. You get two multiplications, A minus E squared, and then minus beta minus ES squared must equal 0. Okay, and then I'm collecting terms for E. E is the energy. Oh, that is the E. Okay, so I'm collecting terms for E. I have a term that does not depend on E. I have a term that depends linearly on E, and a term that depends quadratically on E. All right, so this is basically a quadratic equation in E. And remember, I want to solve for E. I want to know the energy. So what I have to do is I have to find the roots of this equation, which is what I can do with the ABC formula. Okay, so I'm going to apply the ABC formula because this is a quadratic equation in E and solve for E. And this is what I'm getting. I'm finding the roots for E. The first root is alpha plus beta divided by 1 plus S. And there's a second root, and that is alpha minus beta, 1 minus S. Okay, so these are two roots. I get an energy that I'm going to give a plus sign, and energy I'm going to give a minus sign because of the plus and minus sign here. These are the two roots of the equation above. So what does it mean? Well, I can write it out. Let's have a look. Remember, each individual hydrogen atom has an energy of alpha. Okay, each one is a 1s orbital, so E1s is basically alpha. So that is basically the energy of the two individual atoms. I'm going to put them closer, and now I'm going to find two new orbitals, not atomic orbitals, but molecular orbitals that have new energies. One is E plus, and one is E minus. This is E plus right here, and E minus is right here. E plus corresponds to the energy of the positive combination of these orbitals, and E minus corresponds to the negative combination of these orbitals. Okay, and as you can see, these are split now. E plus is lower. That means favorable if bonding happens, and the E minus is higher, not favorable when the bonding happens. It's the anti-bonding orbital. But note that this calculation tells me that the splitting is not equal. Okay, you go down, but you go up more. So the bonding, the anti-bonding character of the function up here is more anti-bonding than the lower function is bonding. It's not equal, and that's basically determined by, as you can see, these values in the denominator as well as how you calculate the numerator. So it's not just an equal split; it's an unequal split. Okay, last thing then, that is the variation principle applied to heteronuclear diatomics. So in that case, alpha A is not equal to alpha B. So I'm going to combine two atoms now that are different. So the situation with hydrogen was kind of easy because, two similar atoms. Electrons come from the same orbitals, 1s, but now I'm going to make it more general and consider a heteronuclear diatomic. In this case, I'm going to make a few assumptions to make it a little easier on myself. S equals 0. This is not true generally, okay? But I'm going to say it anyway, just to simplify the calculation. S is not generally 0, but I can make the assumption anyway and see where it's getting me. And if I do that, and I do the same procedure as above, above means the previous slide, okay? And if I write out the determinant, it's the same procedure, write out the determinant, set it to 0, and I'm collecting terms for E in the equation that follows. You get a quadratic equation in E, and you're going to try to solve it. You find two roots, once again, two roots for E. We're not going to do the whole exercise. It's not really that important. The most important thing is that there's a solution. There's 2 routes for E following the same procedure, okay? And the 2 routes are given right here. And it depends now on a few more things, not just alpha and beta and S, but also, you know, kind of the alpha A and alpha B. So it's a little different. But we still get an expression that is pretty well behaved. I can fill out for A and B using different orbitals, and that's what I've done over here. So I've considered the case here where the first atom is a 1s orbital from hydrogen, and then the second electron comes from a 2pz orbital from F. So this is HF. HF. The 2pz is a little lower in energy, so this energy here will be alpha B. This one will be alpha A. Okay, that's given. That's the alpha A. That's the alpha B right here. You can see that they are not the same. Alpha A and alpha B are not the same. The 2pz is lower in energy than the 1s orbital from hydrogen. Now, if I make linear combinations here, then I get 2 wave functions. This is the psi minus, and this is the psi plus. Okay, this is the first coefficient, Ca, second coefficient, Cb, and the same here. This is Ca, and this is Cb. You see their values are different. They're not the same now. They have different values. First one is 0.28, and the second case it's 0.96, and then here plus 0.96, and here minus 0.28. So there's symmetry, but clearly the coefficients swap positions and they get a negative sign, as you can see. All right, so that is the result of that. And the energies here are as follows. You get a little bit of splitting up for the anti-bonding and a little bit of splitting down for the bonding. Okay, so it's quite asymmetric, as you can see, but you still can compute the energies. This is going to be the E plus, and this is going to be the E minus energy that you can find by just plugging in the values here. Okay, so you can see that you can apply this variation principle for the calculation of the energies of molecular orbitals that are linear combination of individual orbitals from different atoms using this principle. We found 2 cases. The first one was the hydrogen atom, where the 2 alpha energies were the same. And the second case, in this case, HF, is where the 2 alpha energies are not the same. Remember, these alphas are basically HAA. Okay? So this is the new Hamiltonian sandwich between the atomic orbital AA. I don't have a clear solution to this yet. I have to find them. Okay? You can find it in a computer and then plug in the values. But this is the recipe for finding the energies using the variation principle for molecular orbitals. Give it some rest, folks. There's a lot of arithmetic here, but you know, go through it on your own and convince yourself that this procedure is valid and is based on hopefully the principles that you know, I explained correctly enough to you so you can appreciate it. All right, we'll stop right there.